Position, velocity, acceleration. The standard variables of classical physics fail at the subatomic level, where reality dissolves into shifting, superimposed clouds of probability. We cannot use a single number to track a system that exists in multiple states at once. To map this environment, we have to abandon classical equations and build an entirely different mathematical architecture. To pull reliable, testable predictions out of this randomness, physicists rely on a highly specific grammar. We call it Dirac notation. It takes these abstract physical states and translates them into a framework we can solve, linear algebra. Understanding quantum mechanics isn't about visualizing the impossible. It's about learning the mathematical rules that force these systems to behave logically. Every language needs nouns and verbs. In quantum mechanics, the noun is the quantum state, written inside this angled bracket called a ket. The verb is the operator. This represents a physical quantity, like energy or momentum, or a physical transformation acting upon that ket. An operator acts on a quantum state to produce an entirely new quantum state. Looking closely, the ket expands into a column vector of complex numbers. The abstract operator acting on it expands into a literal mathematical matrix. Calculating quantum mechanics is, at its core, the rigid application of matrix multiplication. By converting physical states into column vectors and physical forces into matrices, we convert abstract quantum mysteries into computable math. To use this language correctly, we must follow a strict set of rules. The first is that quantum operators must be linear, meaning they respect both addition and scalar multiplication. As this text explains, a linear operator acts separately on each part of a superposition. If a particle exists in a combination of states, the operator handles each part of that combination individually. In this derivation, an operator A acts on a state composed of 2 parts, 0, and 3 parts, 1. Linearity ensures it distributes perfectly across those internal components. The operator acts predictably, yielding a final superposition that follows the rules of each part. Linearity is the reason quantum mechanics is mathematically solvable. If we know how a force acts on the base states, we can calculate exactly how it will act on an infinitely complex superposition. The second rule is associativity. We can group operations together to simplify the math, but their sequence is strictly locked. Swapping the order is not allowed. Applying operator A, then B, yields a different result than applying operator B, then A. This follows common physical logic. Putting on your socks and then your shoes creates a very different outcome than attempting to put on your shoes and then your socks. In the laboratory, applying a magnetic field and then measuring a particle's spin produces a different physical state than measuring the spin first. This mathematical property is called non-commutativity. It reflects the physical reality that, in the quantum world, the sequence of operations determines the final state. Our third requirement is the Hermitian conjugate, denoted by the superscript dagger symbol. Applying the dagger is a 2-step process. Starting with matrix A containing the imaginary number I, we first take the transpose, flipping the rows and columns. Second, we take the complex conjugate, flipping the positive I into a negative I. This complex manipulation serves a vital physical purpose. Any physical observable in the real world, like an atom's energy or a particle's momentum, must result in a real number. Imaginary values cannot be measured by lab equipment. This gives us the Hermitian operator. When an operator equals its own conjugate transpose, it mathematically guarantees that its measurement outputs will be real numbers. This is why position, momentum, and energy are all defined by Hermitian operators. These operators act as the mathematical bridge connecting the imaginary math of quantum states to the tangible, measurable reality of the physical universe. To move beyond a single isolated particle, we must describe systems with multiple parts using composite kets. We combine these individual states using a tensor product. This operation multiplies 2 separate quantum spaces together to form a single combined system. As this equation block shows, combining 2 individual qubits, which each have 2 basis states, creates a single composite system with 4 distinct basis states. This scaling is the foundation of quantum entanglement. Mathematically, an entangled state is a composite vector that cannot be factored back into its original individual parts. Entanglement is a rigid mathematical feature of the tensor product, providing the framework for quantum cryptography and teleportation. These matrix operations and kets serve as the engineering blueprints for modern technology. Solving the Schrödinger equation using Hermitian operators determines the exact allowed energy states that make organic semiconductors and solar cells function. In medical imaging, MRI machines apply radio frequency operators to the composite spin states of nuclei to generate images of the human body. And in quantum computing, logic gates are linear operators executing matrix math on massive tensor product composite states. We have moved from unpredictable probability clouds to a disciplined system governed by vectors, linear matrices, and Hermitian structures. Every breakthrough in advanced materials and quantum hardware relies on this exact mathematical grammar. Ultimately, Dirac notation and linear algebra provide the rigorous framework required to precisely control the complex quantum world.